Welcome to Pluralsight, everybody. This is LAN Switching Part 2. This is Part 2 in the LAN Switching section for the CCIE Security Written Exam Certification. We're going to talk about spanning tree in this module, and spanning tree is a protocol that is designed for a loop-free topology. Now, we know that we want redundancy in our network. If one path fails, we want to have a backup method. So that's what spanning tree provides for us, ability to have a redundant path in the layer 2 topology without actually introducing some of the shortcomings of having a redundant layer 2 topology. Some of the things that we run into when we have these redundant layer 2 topologies is we will wind up seeing broadcast storms, multiple frame copies, instability of our MAC address database. So with spanning tree protocol, we can have that loop in the topology at a physical level. And within software, we can block the loop, preventing those three issues that I mentioned, broadcast storms, MAC address table instability, and multiple frame copies, and still have a redundant path in case the primary path were to fail. The protocol that we run currently is the IEEE 802.1d spanning tree protocol. This is what's on by default on your Cisco switches, and it creates a spanning tree in the layer 2 topology, and any links that are not part of that spanning tree are going to be disabled. Now, based on an algorithm that was written by Radia Perlman, we will go ahead and figure out a root of the spanning tree, and we will determine the best path for other switches in the spanning tree to reach that root, and then we'll block any ports that are redundant in that path so that we don't form a loop in the network. So the root bridge selection is something that we have to go through first and foremost. If we don't know who the root bridge is, then we can't calculate the spanning tree. Now, the root bridge of the spanning tree is going to be whatever bridge has the lowest bridge ID. Now, the bridge ID is a combination of two values that are concatenated together, and that's the bridge priority, which defaults to 32.768, and the MAC address of the unit. So every single switch is going to have a base MAC address, and then each individual port will have a unique MAC address. That's how layer 2 works. Every physical interface has its own MAC address, but the switch itself has a MAC address called the base MAC address. So we take those two values, we smush them together, we concatenate them, and that becomes our bridge ID. Now, what happens is every 2 seconds, we exchange bridge protocol data units, or what we call BPDUs, and these BPDUs are going to help us to perform an election of the root bridge. And like I said, it's the bridge that has the lowest bridge ID. Once we figure out who the root bridge is, now we can determine the least cost path from other switches back to that root bridge. So we look at all of the ports that we have connected, and the port that's connecting to the least cost path is going to be what we call a root port. The root port is in a forwarding state, and it is our best way to get back to that root bridge. On each segment, remember that's a link between two devices, that's a segment. Each segment is going to have what we call a designated port. Now, designated ports also forward traffic, and any other paths are going to be disabled or blocked. So putting that together, here's what we end up with. You get one root port for every non-root bridge. Every segment has a designated port, and my other ports are disabled. One other little caveat I should throw in there is that on the root bridge, all ports forward traffic. So that means that the root bridge ports would be designated ports because he is the root bridge. The switches that are connected to the root bridge will have root ports, and then, of course, every other port could be blocked, except for one on each segment, which is the designated port.